7. Good morning, everybody. I am Mrs. N Patil, Assistant Professor, Department of Electronics and Telecommunication Engineering, Walchand Institute of Technology, Solapur. Today, we are going to have the discussion on the topic Application Specific Integrated Circuit, that is ASICs. Learning outcomes. At the end of the session, students will be able to understand about ASICs, ASIC design flow. These are the contents of the presentation. So before we start with the presentation, we'll recall digital design which uses logic gates, flip-flops and combinational and sequential circuits. It also has HDL languages like Verilog, VHDL, which describe the circuit behavior. Fabrication technologies like FPGA, ASICs. Importance of performance, power and area in VLSI design. These all has to be recalled before we proceed for the presentation. So digital electronics, which includes logic gates, flip-flops and combinational and sequential circuits which are formed by combining different logic gates, are to be recalled in this. So also flip-flops, which are sequential logic circuits which has the memory and feedback, are also very important to be recalled here. Sequential logic circuits like flip-flops, shift registers and even are the counters are very important. So application specific integrated circuit ASIC, it is a in the design flow is structured multi-stage process used to design and manufacture custom integrated circuit for a specific application. It is complex iterative process that transforms a high level idea into physical chip. There are two main stages: front end design, which is also called as logic or functional design, and back end design. First phase, front end design. This phase focuses on logical functionality of the chip. Back end design is including the phase focuses on the physical layout and placement of the components on the silicon. Front end design. Front end design in the ASIC design flow refers to the initial phase of the chip development where the functionality of the system is defined and implemented using HDL languages like Verilog, VHDL, System Verilog. It mainly focuses on design entry, simulation, verification, and synthesis before moving to the physical implementation. In the front end design, very important step is the initial state is the design specification. Design specification is the starting point. It involves defining the chip requirements, including its functions, performance, power consumption, and physical size. User customer requirements may be like gathering specific needs, like must have the process video at 4K resolutions, and create a high level block diagram for showing how different parts of the chip and overall system will interact. This includes defining bus architectures, memory, interfaces and input outputs. It uses a common language like natural English language and can be redefined using C, C++ or MATLAB for the system level simulations. RTL design and coding is the next step. This stage involves translating the system level design into a hardware description language like Verilog or VHDL. Register transfer level. The code describes the flow of data between the hardware registers and logical operations performed on that data. It is behavioral description, not a physical one. Coding standards. Adhering to the specific coding standards is crucial for synthesis and verification. We can give an example, a simple RTL code that describes 4-bit counter behavior like incrementing by 1 or 1 clock edge. Functional verification. This is very important step to ensure RTL code behaves exactly as the design specification dictates. It is an exhaustive process of testing the design. A separate STL model called a test bench is created to generate input stimuli and check the output of the RTL design. Test bench plays a very important role in the functional verification, which is written using the Verilog coding techniques. So design is simulated using an SDL simulator like Cadence Incisive or Synapsys VCS to find and fix the bugs. Verification engineers use different techniques like code coverage and functional coverage to measure how thoroughly the design has been tested. Back-end design. After once we complete the first front-end design with the verification, specification, RTL coding, we will move for the next step, that is back-end design. Back-end design, or in this phase, it takes the verified logic design and transfers into a physical layout that can be manufactured. So there are various types that are considered in the back-end design. It may be consisting of floor planning, placement, check tree synthesis, clock tree synthesis, physical verification, and STA analysis, or many more. So first thing, logic synthesis. This stage converts the abstract RTL code into a gate level netlist. A netlist is a description of how standard cells like AND or flip-flops are interconnected. A technology specific library containing pre-designed gates is used. This library includes information on the gate's function, size, delays, and power consumptions. The synthesis tool uses timing constraints like clock frequencies and area constraints to optimize the netlist. The result is gate level netlist file and a timing report. Static timing analysis, STA, is a method to check if the design meets its timing requirements without running a simulation. It analyzes all possible paths in the netlist for their delays. The tool checks like timing violations are checked for setup and hold time violations, ensuring that the data arrives at the flip-flops input within the correct time window relative to the clock edge. It identifies critical path, which is the longest delay path in the circuit, and the limiting factor for the clock frequency. STA is a continuous check throughout the backend flow. Flow planning and placement. These are also plays a very important role in the ASIC design flow. First step of physical layout is floor planning, and placement can be defined like this also. It involves defining the overall chip size and placing the major functional blocks and input output pads. The place in this stage, all the standard cells from the netlist are placed within the core area of the chip. The core area is where all the logic will reside. Input output pads are placed on the periphery to connect the chip to the outside world. The power distribution network, VDD, and ground rings is planned to ensure a stable supply to all the parts of the chip. Macro placement. Large pre-designed blocks such as memory, SRAM or DRAM are placed first. Clock tree synthesis and routing. CTS is a critical step to ensure that the clock signal arrives at all flip-flops at the same time, minimizing clock skew. Routing stage involves connecting all the standard cells and macros with the metal wires following the connections defined in the netlist. The tool builds a dedicated network of buffers and inverters to distribute the clock signal in a balanced hierarchical manner. The primary goal is to achieve minimum skew and insertion delays. The routing are of two types, like it is global routing and detailed routing. Physical verification, final and crucial check to ensure the physical layout is ready for manufacturing. Design rule check, checks for manufacturing violations like wires too close together far from each other, that is checked by DRC. Layout versus schematic, this verifies the physical layout exactly matches the logic netlist. It checks for missing or extra connections and devices. Extract parasitic resistance and capacitance from the layout, which are then used for final highly accurate STA. GDS2 generation. The final output of the back-end design flow is GDS2 graphic data system file. This file formats that contains all the geometric informations like shapes, layers, coordinates exactly needed to manufacture the chip. This final is tape out is file is sent to the semiconductor foundry for mask making and fabrication. This marks the end of the design phase and the beginning of the manufacturing process. So, to conclude the session, ASIC design flow provides a systematic path from the specification to the silicon. It ensures optimized performance, power, and area efficiency. A well structured flow minimizes errors and reduces design cost. Thus, ASICs enable high volume, high performance custom solutions. References, there are many books to be referred, and even we can refer the web pages like from the Synapses, Cadence and Mentor Graphics and tutorial points, and some books like written by the Michael John and Kate Bhaar, Neil West, Driver, like books like Digital Integrated Circuits, CMOS VLSI Design, ASIC Design in the Silicon Sandbox, Application Specific Integrated Circuits. So lastly, we provide a special thanks to the Walchand Institute of Technology, Solapur, IDP in Education Technology, IIT Bombay. Thank you.